Imagine a fighter jet that doesn't need a runway or an aircraft carrier. Instead, it accelerates across the ocean on retractable skis before climbing into the sky at nearly the speed of sound. It sounds like science fiction, but in the early 1950s, the U.S. Navy invested millions into making it a reality with the Convair F-2Y Sea Dart. Designed to solve the growing limitations of carrier operations in the jet age, it became the only seaplane in history to exceed Mach 1. Yet despite its groundbreaking design, the Sea Dart was plagued by engineering challenges that no amount of innovation could fully overcome. From violent hydrodynamic oscillations to underpowered engines and structural fatigue, the aircraft became a fascinating lesson in the limits of multidisciplinary engineering. So what exactly made the Sea Dart so revolutionary, and why did it fail? Let's dive into the video. Solving a Navy problem. By the late 1940s, jet fighters were becoming larger, heavier, and faster. Carrier decks designed for piston aircraft struggled to accommodate them. Landing speeds increased dramatically, requiring longer decks and more powerful catapults. Convair proposed a radical alternative. Instead of operating from aircraft carriers, future fighters could take off directly from sheltered bays or the open ocean using a specialized hull and retractable hydro skis. If successful, the Navy could disperse aircraft across floating bases, reducing dependence on vulnerable carriers while dramatically increasing operational flexibility. It was one of the boldest concepts ever proposed for naval aviation. Engineering the airframe. Unlike conventional aircraft, the Sea Dart's fuselage had to function as both an airplane and a boat. Its hull featured a planing design that generated hydrodynamic lift as speed increased, allowing the aircraft to ride on top of the water rather than push through it. The aircraft has a length of 52 feet, 7 inches, or 16.03 meters. It has a wingspan of 33 feet, 8 inches, or 10.26 meters, a height of 22 feet, 9 inches, or 6.93 meters. It has an empty weight of approximately 16,000 pounds, or roughly 7,260 kilograms, a maximum takeoff weight of approximately 22,000 pounds, or 9,980 kilograms. Its large 60-degree swept delta wing wasn't chosen for aesthetics. Delta wings provide exceptional structural rigidity, significant internal fuel capacity, and low wave drag near transonic speeds. However, they also suffer from poor low-speed lift and high induced drag, forcing the aircraft to maintain higher angles of attack during takeoff and landing. Ironically, the Sea Dart spent much of its operation in exactly the speed range where delta wings are least efficient. The revolutionary hydroski system. The most distinctive feature of the Sea Dart wasn't its wing, it was its retractable hydro skis. Instead of using floats or pontoons, 2 water skis extended beneath the fuselage during takeoff. As speed increased to roughly 120 to 145 knots, or about 220 to 270 kilometers per hour, the skis generated hydrodynamic lift, raising the hull clear of the water and dramatically reducing drag. The concept was similar to water skiing, but unlike a skier weighing 80 kilograms, the Sea Dart weighed nearly 10 metric tons. Every wave struck the skis with enormous force. Because water is roughly 800 times denser than air, even modest increases in speed created massive impact loads. Instead of gliding smoothly, the aircraft often began porpoising. This was a violent oscillation where the nose repeatedly pitched up and down as the skis alternately dug into and skipped across the water. Unlike conventional landing gear, which absorbs a single touchdown, the Sea Dart's skis endured continuous high-energy impacts throughout the takeoff run. These repeated shocks transferred directly into the fuselage, increasing pilot workload and accelerating structural fatigue. Twin skis versus single ski. The original configuration used 2 retractable skis. In theory, they distributed weight more evenly. In practice, each ski could strike different wave patterns. If one ski hit a crest before the other, asymmetric forces caused rolling and yawing moments. Engineers later experimented with a single central ski. Surprisingly, it performed better. One ski eliminated differential loading between left and right sides and simplified force distribution through the fuselage. Although the single ski arrangement reduced instability, it couldn't eliminate porpoising entirely because the fundamental interaction between water dynamics and suspension remained. Engineers eventually switched from twin skis to a single ski configuration, which reduced asymmetric loading and improved stability. But the problem was never completely solved. A fighter without enough power. Perhaps the Sea Dart's greatest handicap was its engines. The aircraft had been designed around two Westinghouse XJ-46 afterburning turbojets, each expected to produce approximately 6,000 pounds of dry thrust and up to 7,200 pounds with afterburner. Together, they would have generated around 14,400 pounds of thrust, enough to make the aircraft genuinely competitive. Unfortunately, those engines never became operational. Instead, the prototypes flew with two Westinghouse J-34WE-32 turbojets, producing only 3,400 pounds of thrust each, for a combined total of just 6,800 pounds. That meant the aircraft was operating with less than half of its intended maximum thrust. At its maximum takeoff weight of approximately 22,000 pounds, the prototype's thrust-to-weight ratio was only 0.31. Many successful fighter aircraft of the era exceeded 0.5, giving them significantly better acceleration and climb performance. The Sea Dart simply lacked the power needed to exploit its advanced aerodynamics. Breaking the sound barrier. Despite its limitations, the aircraft achieved a remarkable milestone. On August 3, 1954, during a shallow dive, the Sea Dart exceeded Mach 1, becoming the only seaplane ever to break the sound barrier. However, this achievement came under carefully controlled conditions. Without the intended XJ-46 engines, sustained supersonic level flight remained out of reach. It proved the concept was physically possible, but not practically useful. Structural engineering challenges. Operating from water introduced entirely different stresses than operating from concrete. Every wave created unpredictable impact forces that traveled through the ski attachment assemblies, fuselage frames, hull skin panels, and wing roots. These repeated impacts generated high cycle fatigue, where thousands of small stress cycles gradually weakened structural components over time. Saltwater exposure made matters even worse. Corrosion attacked aluminum alloys, steel fittings, hydraulic systems, and engine components, dramatically increasing maintenance requirements compared with conventional carrier aircraft. The Sea Dart wasn't just fighting physics, it was fighting chemistry as well. Performance specifications. On paper, the aircraft was impressive. It has a maximum crew of 1, a maximum speed of approximately 695 miles per hour, or 1,118 kilometers per hour, a service ceiling of approximately 52,000 feet or 15,850 meters, a climb rate of around 6,300 feet per minute or 32 meters per second, and a planned armament of 4 20mm cannons plus rockets or guided missiles. But these figures represented a machine that never fully reached its intended potential because its propulsion system lagged behind its design. Why it failed. Ironically, while engineers struggled to perfect the Sea Dart, aircraft carriers themselves evolved. Steam catapults enabled much heavier jets to launch safely. Angled flight decks made recoveries easier and safer. More powerful afterburning engines improved conventional fighters to the point where the original problem the Sea Dart was designed to solve had largely disappeared. Also, a tragedy involving the Sea Dart occurred. On November 4, 1954, test pilot Charles E. Richburg was killed when the prototype disintegrated over San Diego Bay during a demonstration flight, which reduced confidence in the program. Unfortunately, the Convair Sea Dart was officially canceled in 1957, and a total of 5 prototypes were manufactured by Convair, though only 3 ever took to the water for flights. Conclusion: the F-2Y Sea Dart wasn't a failure because its engineers lacked imagination. In many ways, it was one of the most ambitious aircraft ever conceived, combining naval architecture, aerodynamics, hydrodynamics, and jet propulsion into a single machine. In the end, the Sea Dart became a reminder that engineering isn't just about proving something can be done. It's about proving it can be done reliably, efficiently, and better than the alternatives. And while it never entered service, its legacy lives on as one of aviation history's boldest experiments, a fighter jet that dared to turn the ocean into its runway and for one brief moment succeeded. Thanks for watching this video. Remember to drop a like and subscribe for more, and we'll see you in the next one.